everybody. We're Team 3, and this is our final presentation. Here's the overview of our problem. Invisible watermarking methods on generated images. So invisible watermarks embed messages into either the pixel or latent space of the images in order to allow detection and identification of AI-generated images. On the other hand, attacks on these watermarks aim to remove the watermarked information while preserving as much image quality as possible. Our goals with this project is to improve both sides of the watermarking problem. We investigate how to make watermarking more robust by combining different watermarking modalities, that being image space and latent space, which is something that has not been tried before. On the other hand, we investigate how to make attacks degrade less of the image quality by only applying attacks to localized patches of the image, whereas current research only uses attacks to target the entire image.
So as previously mentioned, we're taking a novel approach of combining two previous approaches, tree ring and stegastamp, and then we're using localized attacks. For this, we'll be using the MS COCO 2017 validation split dataset. It has 5,000 images of common objects in context, and for evaluation metrics, we'll be using detection rate and image quality in the form of FID.
First, let me briefly introduce the conventional watermarking method. Stegastamp embed a watermark by passing an existing image and a message through an encoder, and then use a corresponding decoder to extract the image. In contrast, the tree-ring watermark method embeds the watermark during image generation by incorporating a message key into Fourier transform noise. According to reference, stegastamp greatly perturb the latent space, which is where the tree ring message is encoded. Vice versa, tree ring greatly perturb the image space, which is where the stegastamp message is encoded. This means stacking the two watermarks may cause one to destroy the other. So we test two approaches, naively stacking and a remover architecture. The first approach embeds a stegastamp directly onto a tree-ring watermarked image. We expect the stegastamp's residue to interfere with the tree-ring watermark, leading to a second approach. In this second approach, we train a remover network to remove the stegastamp watermark while preserving the tree-ring watermark. This reduces interference from stegastamp so that we can decode the tree-ring watermark more clearly.
Onto the localized blurring attack method, where we focus on the way that stegastamp encodes information in the image. As we can see, there's more information encoded on the kayak and the people in the kayak than the rest of the image. We can use this information to direct our localized attacks. Here's our pipeline for localized blurring attacks. We run the watermarked image through the stegastamp decoder with GraCam to get a heat map of hidden information, and then pass it through a top percentile masking function to output the regions of interest which our attacker uses to attack. The output has blurred regions corresponding to the regions of interest.
Here we evaluate the effectiveness of our stegastamp removal process. The table compares the two key metrics, bit accuracy and overall accuracy, before and after the removal process. Our results show that the stegastamp watermark is no longer detectable after removal. This means that we have reverted the image to just the tree ring watermarked image. On this slide, we examine the detectability of tree ring under different scenarios. First, we see that under both approaches, the tree ring watermark is unaffected by the modifications from stegastamp. However, we are respecting approach 1 to make the tree ring watermark undetectable. The only slight worse p-value for approach 1 shows that stegastamp does affect the latent space, but not as much as we initially expected.
So on to the results for localized blurring attacks. First, we ablated on blurring kernel size. You can see as we increase the kernel size, more of the image is destroyed. And then we ablated on percentile thresholds. And you can see as the threshold gets higher and higher, less of the image is attacked. So then for comparing our attack against the two baselines, we see that it has similar detection rate to straight blurring, but a significantly better FID, or in other words, image quality. And then comparing it to the regeneration attack, we can see that our detection rate is around the same, but then our FID, or image quality, is significantly worse. So why is this the case? Well, it's because we use a higher distortion attack, blurring, and attack less pixels. So in future work, we could try replacing blurring with regen to see if it has similar benefits. So in conclusion, we successfully showed that it's possible to combine stegastamp and tree ring without one destroying the other. And then we also found that LBA decreases degradation compared to full image blurring. So here are our references. Thank you for listening.